This is a bonus third segment to the answer to practice question 3 from week 2. And I'm partway through answering question 3F. In the previous segment, we saw a little simulation where I was taking samples out of a known population and then calculating the sample mean. And we saw how that sample mean calculation varied depending on which particular values I'd sampled. And we also saw, just to go back to it, that it looked as though if we had our population distribution was this blue line, that when we randomly sampled elements from that population, 5 elements in this example here, and then calculated their sample mean, that those sample means, if we plotted the values that they could take, they seemed to follow a distribution that was roughly like this orange line, that had the same central values, the same mean, and also but a lower distribution. A lower dispersion. The orange curve is not spreading out anywhere near as far as the blue population curve. Okay, so let's have a look at what the central limit theorem says. It says that if you select n values, independent random values, that all come from the same PDF. That's what was happening in that example I gave before. My probability density function, if you like, was those blue dots, and I was I drew 5 independent values out of that distribution, and I knew what the mean of the population was, and I didn't show you that, but I could easily have calculated its variance. And we repeatedly we calculate the sample mean for those n values. So the central limit theorem says, if you do that, it then says if this value of n approaches infinity, or as it approaches infinity, as our sample size gets larger, then the values of the sample mean that we will come up with, if we take repeated samples, will be normally distributed with a mean that is the same as the population mean, but a variance that is equal to the population variance divided by n. Dividing by n, and in our case n was 5, so it was pretty small. Dividing a number by something greater than 1 will mean that the result is smaller than the numerator. And furthermore, the central limit theorem comes in a different flavor. It says that if you calculate a standardized score for each sample mean that you calculate, so Z is representing a standard normal value. So it's saying calculate your sample mean, so choose 5 in our example and calculate their sample mean. Then take away the population mean, so that was about 60 in our example, and then it says divide by the standard deviation of your sampling distribution, which was the orange graph that I showed you earlier. Now remember, that sampling distribution has a variance equal to this number, and its standard deviation will be the square root of that, which is this result here. So we've gone from a sigma squared to a sigma, dividing by n to dividing by the square root of n. So if we do that for each of our sample observations, sample means that we calculate, then the distribution of those standardized scores will be the standard normal distribution. So a normal distribution with a mean of 0 and a variance of 1. Okay, so that's some background theory. Let's use it to finish off answering the exercise from week 2 workshop, which is the third question for the practice questions. So this is where we got to in the first segment. We just calculated a whole lot of sample means, and we calculated that their mean is 4.96, and their standard deviation of all these sample mean calculations is 0.399. So the central limit theorem says that that mean should be 5, which is the mean of the uniform distribution from which we were drawing these values down here. And it says that the standard deviation should be equal to the standard deviation of the population divided by the square root of n, where n is the number of observations that we have in each sample. So that I think the standard deviation for the uniform distribution I had calculated earlier in answering this question. It was that value there. So I'm just going to say equals and then go and click on that thing. And then the central limit theorem says that we should divide that standard deviation for the population by the square root of the number of observations in a sample, which was 20. So you can see that didn't come out to be as close as I was expecting. And what have I done wrong? Or have I done something wrong? Yes, I have. I've actually chosen the number of samples that we took, but what I should have been doing was the number of observations in each sample, and that's down here, 50. So if I correct that, what do I come up with? A number that is very close to what we found in our little experiment. So, just to reiterate, we chose, in this first sample, 50 random values from a uniform distribution which range between 0 and 10. And then we repeated that here. Chose another 50 values from that distribution, and so on. We did it 20 times. For each of those, we calculated the sample mean. And the central limit theorem says that those sample means should be distributed with the same mean as the population. So that's the population of the uniform distribution, 5. The mean of our sample means was very close to that. So that's it seems to be, the story seems to check out so far. And then the central limit theorem says that the standard deviation of all these sample means should be equal to the population standard deviation divided by the square root of n, where n is the number of observations that you have in calculating each sample mean. And again, we're seeing a very small divergence here between the standard deviation of these sample means and the one that the central limit theorem predicts. Okay, G says, of the question says, standardize each of the sample means you calculated in E, so that's these. To standardize them, how do you get a standardized score? Well, you take the score, and I'm actually going to put brackets around that. You take the score, you subtract its mean, which should be this value. If I didn't actually know what the population parameters were, I could have just taken the sample numbers that I had, but seeing as I do know what the population should be, I'm going to use that. And then to finish your standard score calculation, you divide by the standard deviation, which is this for the population. And because I want to copy this formula across, I'm going to put a $ in front of that B and a $ in front of that C. And then I'll copy it across. Okay, so what I've just done here is I've converted that value there to a standardized value, that value there to a standardized value, and so on. So these things here now represent 20 standardized values. And part H says calculate the mean of those standardized values and their sample standard deviation. So I'm going to just copy those formulas, Control C, paste them down here, Control V, try that again, Control C, Control V, and I'll just check that I'm doing the right thing. Yes, so it's referring to that formula seems right. I'll double click on that. Send D, yeah, it seems to be doing the right thing. Okay, so then H says compare your results with the values predicted by the central limit theorem. So the central limit theorem says that if we standardize each of these sample means calculations, then we expect to end up with here the standard normal distribution. which has a mean of 0 and a variance and a standard deviation of 1. And you can see that our standardized values do have a mean that's just a fraction under what the central limit theorem predicts. It in fact predicts that when n gets very large, so we've only got n being 50 here, and we're already getting a result that's very close to it. And also the standard deviation that we got for these values is very close to what the central limit theorem suggests. Finally, this question says to produce a histogram, that's I, of these values. So just quickly, that will be data analysis, histogram, okay. The input range is going to be, I'm going to click on that first standardized value, control shift right arrow. The bin range, I might leave that blank for now, just let Excel automatically calculate it. The output range, I will get it to produce this in a new sheet. I'm going to call it standardized histogram, and I do want chart output, so okay. There it is there. Excel has automatically chosen four bins only, and so it's very difficult to see the distribution with such a small number of bins. So I might actually just go back to part D that we were working on, which is now spanning to part I. I'm going to select some bins here, and I know that the standard normal distribution ranges from roughly -3 to roughly +3. So I'm going to start off with a lower bin of -3. I'm going to go up by increments of 0.5. So I just typed equals the cell above plus 0.5, and now I'm going to drag that down, and I'll probably stop at 3. And you can see that I've now got some bins that range between -3 and 3. Let's draw a histogram for that. Same input range. The bin range I'm now going to manually select, and it's going to be these ones. I've left out the bin's head label because I didn't have a label for the X values that I was wanting to graph. I'll call this standardized histogram 2 and put it in a new sheet. Now let's see. Now, in theory, that should be looking like the standard normal distribution, but bear in mind that we've only observed 20, we've only selected 20 values from the distribution in coming up with this histogram. You can see that it sort of like perhaps presents a sketch or a rough outline of the normal distribution. It does seem that most observations are in this region of around 0, and we know that the standard normal distribution has a mean of 0. And we certainly don't see any observations beyond +3, nor, in fact, I think that's below, or none below 3. It's not looking perfectly symmetrical, but another one observation out here, for example, if the next observation had been in this range here, we would probably be more happy to say, yeah, that looks symmetrical. It looks sort of exactly like I would expect for a standard normal distribution. So I'm going to say with a small number of observations, this histogram is not looking too dissimilar to what was expected, which is the standard normal distribution. And that is the end, at last, of question 3.